Good afternoon, friends. Hello. Am I audible, friends?
Good afternoon, sir.
Good afternoon. Are you able to see the whiteboard? Hello.
Yes, sir. It's
Are you
visible,
able
sir.
to hear me?
Yes, sir.
Are you able to see the whiteboard and me?
It's visible, sir.
Okay. I think numerical methods class is also over, right? Both the classes, methods of applied maths and numerical methods classes, they are over, right?
Yes, now, sir.
Okay. Bhujan Jessarandi, Srilat Garu, have you taken lunch?
Yes, sir.
Okay. Right. Yeah. Yesterday, we were proving this theorem, right? The space beyond n dash is complete if...
Tell me the page number, sir.
Yes, please. Page number maybe 66, is it?
Thank you, sir.
Yeah, it is page 66, 3.4.3. Theorem 3.4.3. I am not writing this statement completely. I am taking only part of it. B of n dash is complete if n dash is complete. Okay, this is the final part of the statement of this theorem 3.4.3. Okay. In fact, yesterday I showed that this space is a vector space. This set is a vector space. Okay, what is this set? This is the set of all linear maps n from n to n dash, which are continuous. Okay, T is continuous on n. Okay, so B of n and n dash are linear spaces or vector spaces for the same field F. Okay, they are vector spaces for the same field F, right? And then T is a linear map from n to n dash, and T is continuous. Means it is a bounded linear map. Means what? There exists an m greater than 0 such that norm Tx is less than or equal to m times norm x for all x in n. Okay. If this happens, then this is linear. Then the linear map T is said to be bounded linear map. By bounded linear map, we mean this. Okay, T is linear, and this is true. Okay, the norm of the image T image values are bounded by a constant times norm of x. Okay, so now, so you correct all such bounded linear maps T on n. Means boundedness, this boundedness is also equivalent to continuity of T on n. In fact, it is also equivalent to continuity of T at origin, at the zero identity, A2 identity of n. Okay, so you correct all such continuous linear maps. The set of all of them is denoted by script B of n dash. Okay, yesterday we showed that this is a linear space. The set is a linear space. Okay, and in fact, on this set, norm T is equal to supremum. Is equal to supremum of norm T of x such that x belongs to n and norm x is less than or equal to 1. Okay, you take the supremum of norm Tx, where x varies over n, the domain of T is n, and then norm x is less than or equal to 1. X come from the closed unit sphere around the origin in N. Okay. On that closed region, you find T of X and then find the norm and find their sup. This is defined as norm T. Okay. Yesterday we showed that this is a norm. This is a norm on this. Okay. Is a norm on the script B of N and dash. This we showed. Okay. I was proving this statement that if N dash is complete, so is this linear space, this normal linear space. That's what I was trying. So I could not finish it yesterday. I could not finish it yesterday. Today I will finish it. Okay. So this is all background. Okay. So let us assume that N dash is complete, and we'll prove that this normal linear space is complete. What do you mean by complete? Completeness means that every Cauchy sequence in N dash is convergent. If you have a normal linear space, that normal linear space is said to be complete if every Cauchy sequence in that is convergent. So we have to take to show that this is assumption. This is assumption. This is hypothesis, and this is assertion. This is the conclusion. Okay. So to show that this is complete, we start with a Cauchy sequence in this normal linear space. Okay. Yeah. So let Tn where n equal to 1 to infinity contained in the space B of N and dash be Cauchy. Okay. This is a sequence of linear maps. So you have to take a sequence. This is a space of linear maps. So to take a sequence in this space of linear maps, right? That is Tn. These are continuous linear maps. Okay, we have and to show that this is complete, we have to start with a Cauchy sequence. Okay, therefore, for all epsilon positive, there exists an n naught belonging to n. I'm writing the definition of quotients. Okay, for every epsilon positive, there exists an n naught belonging to n. For all n comma m, Tn minus Tm is less than epsilon. Okay. Right. What is the meaning that this is Cauchy? For every epsilon positive, there exists a natural number n naught such that for all n comma m greater than or equal to this natural number n naught, the norm of the difference of Tn and Tm can be made less than epsilon. Means these two functions come arbitrarily close. Okay, leaving a finite number of Tn values. Okay, T1, T2, we are leaving T1, T2 up to Tn naught minus 1. Okay, T1, T2, we are leaving all these. How many are there? There are infinite. If you leave these n naught minus 1 number of entries, still they will be infinite. Among the remaining, we want them to be as much close as we want. Okay, this is called they come near sufficiently close. Okay, yeah. Okay. Now, what happens? Yeah. Look at this. What is this? What is this norm? Norm Tn minus Tm. What does this mean? This is supremum of norm Tnx minus Tmx. Okay. As that x belongs to n and norm x is less than or equal to 1. Okay. Tn is a continuous linear map. Tm is also a continuous linear map. Okay. So Tn minus Tm also becomes a continuous linear map, right? Because it's a linear space. Okay. So Tn minus Tm will be present here. It is continuous linear map. So and for that you can define norm. Okay, because this is present in this, you can apply norm which acts on this. So apply norm for this function which lies here. So it is what, by definition, this norm is supremum of evaluate these this function at x. Okay, that is Tn of x minus Tm of x. And where x comes from, it comes from the closed unit sphere around n, around origin in n. In n, these are the points x which lie in the closed unit sphere around origin, and x come from n. Okay, so this is definition. Now because this is super for all this, it is greater than each of these. Therefore, for x belonging to n, norm x less than or equal to 1, norm Tnx minus Tmx is less than or equal to norm Tn minus Tm. Okay. Why? Because this is defined as supremum of all these. It will be, this sup will be greater than or equal to each of these individual ones. That's what I wrote. This is supremum. Supremum is taken over all these values. As x varies, this value may vary. Okay. And it will be greater than, supremum will be greater than each of these individual values. That's what I'm writing. Supremum is greater than each of these individual values. Okay. Now you apply this. Right? This is less than epsilon for all n comma m greater than or equal to n naught. Okay. So, right? The norm of this difference is less than epsilon for this kind of n and m. Okay. Now, what this means? The norm of these Tnx and minus Tmx is less than epsilon. Okay. For n comma m greater than or equal to n naught means the sequence Tnx where n equal to 1 to infinity is Cauchy. Okay, what is the meaning of this? Tnx is Cauchy means what? You start with an arbitrary epsilon. There should be a natural number n naught such that for all n comma m greater than or equal to n naught, the difference between the Tnx and Tmx in norm must be less than epsilon. Okay. So we are obtaining that this sequence Tnx is Cauchy because of this. This is less than epsilon. Okay. And where do these Tnx lie? Tn's are mapping what to what? They are mapping n to n dash. Okay. Tn's are mapping n to n dash, right? Tn's are mapping n to n dash. So they take x in n to Tnx. Okay. So Tnx are points in n dash, and n dash is complete. By assumption, n dash is complete. This is hypothesis. N dash is complete. In this complete normal linear space, we have got a Cauchy sequence. Tnx is Cauchy. So it has to converge because n dash is complete. Tnx has to converge. Okay. That's how it is Cauchy and lies in n dash, which is complete, n dash complete. Okay. By hypothesis, n dash is complete. And this sequence lies in n dash. Therefore, this will be convergent. Because this sequence is complete and this is Cauchy, this has to converge. That is the property of completeness. Therefore, this will be convergent. Therefore, Tnx is convergent. Okay, and then we define T of x. T of x is equal to limit Tnx as n goes to infinity. Okay. Right. Now this is convergent. So take the limit of this. Okay. And define this as T of x. For every x, Tnx converges. So define limit of Tnx as Tx. And yesterday we showed that this Tx is T belongs to B of n. Okay. This belongs to B of n comma n dash. Okay. Yesterday we showed that this T is linear and is also continuous. That's how T belongs to this. Okay. Now we we collect this one. Okay. Now we'll show that this Tn, the sequence Tn converges to this this T, the T we have defined. We'll show that the sequence Tn converges to T. Claim Tn converges to T in the normal linear space B of n and dash. Okay. On the linear space we have a norm. Okay. In that norm, we'll show that the sequence Tn converges to this T. Right? Okay. How can we do that? What do we have? We have that Tn is quotient. So let us take this statement. Okay. So this is true. And here what we do is we fix n and let m go to infinity. We fix n and n greater than n naught and let m go to infinity. So this Tm will be approaching T. Okay. So we call this one. So in this, in one, this is proof. In one, let fix n greater than or equal to n naught and let m go to infinity. Okay. So we don't let n vary. Okay. We fix n and we let m only vary in this. So as m goes to infinity, Tm goes to T. That's how we define it. Okay. As m goes to infinity, Tm goes to, right? Tnx goes to Tx. So yesterday we showed that Tn goes to T. Okay. So what happens? So let me write. Right. So then what happens? Let us write this statement. Okay. What happens to this? So one changes. So for all n greater than or equal to n naught, and of course epsilon is positive, there exists n naught. Does that? For all n greater than or equal to n naught, norm Tn minus T is less than epsilon. Okay. Right. One minute. Okay, let us prove this. Okay, this is it. Yeah. Okay. So this we have to do in norm Tmx, in norm Tnx minus Tmx. Let us take this sequence. What happened? This norm. Yeah. Let us take this one. In this we have to apply. Okay, because we have to. This is Cauchy sequence. In this, right? This is the meaning of Cauchy sequence. So in this, we fix n and let m in turn to infinity. Not this. I'm sorry. Let me change this. This is one. Okay, this is one. This statement is one. Okay, in this statement, you fix n and let m go to infinity, and then you will have a norm of Tnx minus Tx is less than epsilon. Okay, is less than epsilon. So let me make change. So yeah. So I'm applying. In this equation. In this equation, I am fixing n and let m go to infinity. So then we have norm of Tn minus Tx is less than or equal to epsilon. Okay. So let me write that. So the norm of Tnx, norm of Tnx minus Tmx, right, is less than right. Norm of Tmx minus Tx is less than or equal to epsilon. Okay, so look at this. In this equation, I am fixing n and letting m go to infinity. So this goes to t. I can write norm of t and x minus t is less than or equal to epsilon. Okay, that's what I wrote. Norm of t and x minus tx is less than or equal to epsilon. Okay, and then yeah. Now let us consider norm of this one. Right. Let us look at this. What is norm of Tn minus t? We have to show that Tn converges to t. In which norm? In the norm of this. So take the norm in this normal linear space. That is norm Tn. How did we define this? This is supremum of norm Tnx minus Tx. Okay. As x belongs to n and norm x is less than or equal to 1. Okay. How is the norm defined? You take the difference of these two, apply norm on that. Okay. And by definition, this norm here is supremum of, you evaluate this at x, where x comes from n and this closed unit sphere around the origin. Okay. Now, because of this, this individually less than or equal to epsilon. So this will be less than or equal to supremum, right? Supremum. Okay, this supremum also will be less than or equal to epsilon. Each individual candidate is less than epsilon, less than or equal to epsilon. So sup also will be less than or equal to epsilon. So you have, this is less than or equal to epsilon. Okay, for all n greater than or equal to n naught. Okay, there exists n naught, right? And so because of this, sup also will be less than or equal to epsilon. Okay, sup will be less than epsilon, less than or equal to epsilon. And what are n values? They are greater than or equal to n naught, and n naught is a fixed natural number. Okay, this means that this is the definition of convergence of Tn to T. What do we mean that this converges to this? Given epsilon positive, there should be a natural number n naught, such that for all n greater than or equal to n naught, the norm of the difference between these two, that is Tn minus T, must be less than or equal to epsilon. So we have obtained this. Okay. Therefore, norm Tn minus T tends to 0. This means what? Therefore, Tn converges to T in this normal linear space. Okay, right? So that's how we show that this quotient sequence is convergent. Therefore, B of nn dash is complete. Okay. So what we did, let's recollect. So we started with this space of continuous linear maps from n into n dash. We assume that n dash is complete. Okay, and we are trying to show that this normal linear space is complete. Okay, to show that this is complete, we should show that an arbitrary quotient sequence in this normal linear space is convergent. So take a quotient sequence in this. You take a quotient sequence Tn in this normal linear space. Right? What is the meaning of this? It means this. For every epsilon, there will be a natural number n naught, such that for all n and m greater than or equal to this, the difference of the corresponding Tn and Tm, this difference in norm will be less than epsilon. They come sufficiently close. Okay. Yeah. Now, what is the meaning of this? This norm, it is sup of, evaluate this x, where x are coming from n and norm x is in this closed unit sphere. Okay. And then for these x values, you consider, Now this sup of individual values. It will be greater, this sup is greater than or equal to each individual value. I have taken these individual values. This is less than or equal to norm, this, because of the sup, it will be less than or equal to this. And this is less than epsilon. Okay, for all n comma m greater than or equal to n naught. Right? Now, it means this is Cauchy. T and x are Cauchy. Because you have epsilon here, and n comma m are greater than or equal to n naught, and epsilon is arbitrary. It means T and x is Cauchy. And where are T and x? Tn's are mappings from n to n dash. So it takes Tn takes x to Tn x. So Tn x belong to n dash, and n dash is complete. By hypothesis, n dash is complete. Therefore, Tnx being a Cauchy sequence, it has to converge in n dash. Okay, so Tnx will be convergent, and this limit exists. Okay, and you define this limit to be T of x. Yesterday we showed that this T becomes linear and is also continuous. Okay, therefore it will be in this space of continuous linear functions from n to n dash. Now we are showing that the sequence Tn in fact converges to this continuous linear map T. Okay, to do that, we look at this inequality. In this inequality, we fix n and let n go to infinity. Though, and because norm is continuous, norm of limit of this will be norm of Tn of limit of this. This is constant. This is changing. So limit of this will be norm of Tnx minus limit of this. That is T of x. So that's how you have norm of Tn minus Tx will be less than or equal to epsilon. And you take limit, it will be less than or equal to epsilon. Okay. So this means what? This means, so then you consider the norm of this, the difference of these. Okay. It is what? Supremum, evaluate this at x, where x comes from n and from the closed unit sphere. Okay. And because of this, this is true for all x. What are x? X are coming from n and norm x is less than or equal to 1. Okay. So for x belongs to n and norm x is less than or equal to 1. Okay. Now, when you take supremum, the supremum of all these will be less than or equal to epsilon. Okay. For which n values for all n greater than n naught, there exists an n naught. Okay. We started with an arbitrary positive epsilon, and we could obtain that norm of that there exists an n naught, such that for all n greater than n naught, norm of Tn minus T can be made less than epsilon. This in fact is a meaning of the convergence of this in this norm. Okay. So norm of Tn minus T goes to 0 means Tn converges to T in the norm of this. Okay. We took this to be a Cauchy sequence, and we are able to show that it converges to a point in this. Okay, because this is present in this. Okay, that's how B of n dash is complete. Okay, so that's how when n dash is complete, we show that B of n dash is complete. Okay, yeah. Now let's enter the next chapter or unit 4. In this unit, you talk about compactness. Okay, and unfortunately, compactness is not defined there. So I'll try to explain. In fact, you know what you mean by compactness from topology. You'll be knowing. Okay, let I will explain what we mean by compactness. Okay, say we have a normal linear space. Say V is a normal linear space. V is a normal linear space. Okay, so this is V, right? And V is a normal linear space or a field F. Okay, and then in this you take a subset capital A. Capital A is subset of n. Okay, I'm taking subset capital A in this normal linear space. Okay, so A is contained in V. To show the compactness, what we mean? Can anybody say what is meant by compact? A is compact in V. When do we say A contained in V is compact? When do we say this is compact? How do we define compactness? You take an open cover for this. For A, you take an open cover. You cover A with open sets. Okay. And if, so if you can cover A with open sets, right? Then if every open cover of A has finite subcover, means out of the sometimes these open sets which are colored red may be infinite in number. But compactness says that out of these infinite numbers, only finite number of open sets are enough to cover A. Okay. So compactness means every open cover of A has a finite subcover. Okay, that's what is meant by compactness. Compact and A is said to be compact, of course, in V. If and only every open cover of A in V has a finite subcover. Okay, right? You take, see, this A may be covered by open cover means A is covered by open sets. There may be infinity in number. These open sets, red colored sets may be infinite in number. Those are all open sets in V. Okay, but if your A is compact, out of this infinite number of open sets, you can take only finite number of open sets, and their union will be covering A. That is called a finite subcover. Okay, and that should be true for each and every open cover of A. Okay, if that is the case, we say that A is compact. Okay, let us look at this example. On the number line, let us take a closed interval A comma B. Okay, on the real line, you take a closed interval A comma B. Okay, I'm taking A is less than B. Right? And for every point, how many points are there between A and B? How many points are there? Friends, can you tell me how many points are there between A and B? Hello? Is there anyone?
Infinite, sir.
Infinite number of points are there. Okay? Yeah. So around each point, if you have X here, you take X minus delta and X plus delta. You take this open interval. Around each point, you take an open interval. Okay? You take an open interval. Around each point, if this is your X, okay, around each X, you take an open interval. Okay? And this open interval, for this open interval, midpoint is X. Okay? And this open interval is open. So this closed interval A comma B is contained in these open intervals. This delta may depend on X. So it is delta X minus X comma X plus delta X, right? As that. Where from X comes from? Where from X comes? X belongs to A comma B, okay, comma, there exists a delta X positive, okay? But except, yeah, for each thing, and another condition is that this should lie in the closed interval A comma B. Except these last two things. For A, I allow the closed interval to go out. Okay, the open interval to go out. For B also allow the open interval to go out. But for everything else, they will be containing these open intervals will be contained in this closed interval. Okay. For A, I allow A minus delta X, delta A, comma A plus delta E. This may go out. This may go out. Okay, union. And this is what? This is B minus delta B, comma B plus delta B. Okay, these points may go outside this closed interval. Okay, so, but still, this is open. This is open. In R, the open intervals are open. So, this becomes an open cover. This becomes an open cover. This interval, and these open intervals. These all these together cover AB. So, because the points are infinite, this is an infinite open cover of AB. And this is a finite, this is closed and bounded. A closed interval is closed and bounded. It is bounded because length is finite. Okay, it is bounded. So in R, this becomes compact. If a set is closed and bounded in R, it becomes compact. And every compact becomes closed and bounded. Okay, so out of this infinite open cover, only finite number of intervals are enough to cover this one, okay, because of compactness. So that is the strength of compactness, okay. And out of this infinite number of intervals, it is enough to deal with a finite number of these which cover this closed interval, okay. That is the strength of compactness. In fact, here we are saying that closed and bounded sets are compact. So we have this. We have a theorem called Heine-Borel theorem. Heine-Borel theorem. Okay. Before that, previously I forgot to tell you, these n dash are called, here you have a point to remember. If your n dash is the field itself, right? If your n dash is the field itself, then we say we denote it by n star, and this is called the dual of n. Okay. If your n dash is the field itself, okay, then B of n dash, right? B of n dash is called dual. If this is field, then B of n comma f is called, right? Here I can write f. This is B of n comma f. Okay. This is the set of all continuous linear functions from the space n into field. Okay. This is the set of all continuous linear functions from the space n into field. Okay. If we are taking field to be f to be R or C. In each of these cases, these are complete. These are complete normal linear spaces. Right? These are complete normal spaces. Right? Individually, each of these two is complete. Okay. So yeah, because f is complete, we know that if n dash is complete, this also will be complete. Okay. That's how n star will be complete. This is complete. Okay. So you have to remember this. In the exam, you may be asked to prove this, that n star is complete. You have to show that when n dash is complete, and because n star is what? This one, with n star equal to f, where f is field. Because for field we take these two, any of these two, because these are complete, your n star also becomes complete. This is called dual of n. Okay, you have to remember. Okay. Now let me come back to this. Yeah. We are talking about the Heine-Borel thing. Okay, it says as follows. Let A be a subset of Rn. Okay, I'm taking n-dimensional space. N is a natural number. I'm taking a subset A of Rn. So A is closed and bounded. A is closed and bounded. If and only bounded. If and only A is compact. Okay. In the n-dimensional space, in the n-dimensional Euclidean space or the real space, a set capital A is compact if and only if it has to be closed and bounded. Okay. In your topology, when you studied topology, you might have shown that a compact set has to be closed. Okay. You may recall. In fact, every T2 space, right? A compact set in a T2 space, Hausdorff space is closed. Okay, a compact set in a Hausdorff space is closed, and every metric space is T2. Every metric space becomes T2. Okay. Every metric space is T2. Space is T2. How? See, what is meant by T2? See, if you have a topological space, right? If x comma tau is a topological space, what is meant by T2? You take any two distinction points. X and y. You will be able to separate this with the help of two disjoint open neighborhoods. Okay, so here you can find an open neighborhood around x. Here you can find an open neighborhood around y, such that these two are disjoint. These two neighborhoods don't have any common element. Okay, Okay, and this is true for each and every distinct points x and y of x. Okay, so that's what you mean by T2. T2ness means every disjoint pair of points can be separated with every distinct pair of points x and y can be separated with disjoint open neighborhoods. Okay, that is what is meant by T2. And if you have a metric space, you are inside, right? You have some metric on it. Okay, and this becomes T2. Every metric space is T2. Every metric space is T2. How? You take any two distinct points, x and y. Okay, and what is the distance between x and y? It is d of x comma y. I'm assuming x and y are distinct, so this has to be positive. This distance has to be positive. Now, what you do is, now you take an open sphere around x and an open sphere around y, such that the radii, right, Rx and R1. Rx. In fact, you can take the same radius, no problem. Okay, you can take the same radius. You choose R to be less than d of x comma y by 2. D of x comma y is a positive number, so choose your R to be less than 2. Okay, less than half of this. So midpoint will be somewhere here. This is the d of x comma y. Midpoint will be somewhere here. Okay, if this length, if this radius is less than this half of this distance, then this open sphere and this open sphere does not intersect. These don't intersect. Okay, so if you choose R like this, in this case, S R of x intersection S R of y is empty. Okay, because of this, in any metric space, if you are given two distinct points, you can separate them with the help of open neighborhoods. You can separate them with the help of open neighborhoods. Okay, these are open neighborhoods. This you can do in a metric space. Therefore, a metric space is T2. Okay, and we have this theorem. This SRINIVAS. Now let me show that if we have a compact set in a metric space, it is closed. Okay, that's what I am trying to show. A compact set in a metric space, in a T2 space. Okay, in a T2 space or metric space is T2 space is closed. Closed. And if it is metric, you can say that it is bounded. Okay, let me take metric only, no problem. Let me restrict to metric. Okay, so in a metric space, a compact set in a metric space is closed and bounded. Okay, how can you do that? How can you do that? This should be it's closed and bounded. This should be a compact, a finite, a proper compact set. It has to be a proper subset. It has to be a proper subset. Otherwise, also it's okay, no problem. Okay. Otherwise, also no problem. How? Say A is a subset of X. Okay, this is A. So you take if A is a whole space, then it is closed. If capital A equal to X, it is closed. If suppose A is a proper subset of X, so there will be a point outside. There will be a point Y outside this A. Okay. Now I'm assuming A is compact. I'll show that A is closed. What I do is I'll take a point here. X. Okay. Now X in A. Now X and Y is lying in the complement of A. So X and Y are distinct. Now you take up in metric space you can take two distinct open neighborhoods which are disjoint. Okay, this you can do because your metric space is the T2. You can separate X and Y with disjoint neighborhoods, and you can also take Okay. Now you do this for each and every X coming from. Say you take every another element from A and take this element X2 and Y. they can be separated with the help of two open neighborhoods. Okay, disjoint open neighborhood. You take another point here, x3, this x3 and this y can be separated with the help of two disjoint neighborhoods. Okay, now, so if you let your x vary in A, you'll be getting different neighborhoods here. So this A is contained in union of all these open neighborhoods. Union U such that U is a neighborhood of X, as X belongs to U, A. Okay. For every X, you can find an open neighborhood U. This is U. You collect all such U's. So A is contained, and you are letting X vary over A. So your A will be contained in U. And you are assuming A is compact. So this is an open cover. An open neighborhood is open. So this is an open cover. Because of compactness, compactness gives that there exists a U1, U2 up to some UN, such that A is contained in U1 union U2 union UN. Okay. Out of these, you can take finite number of entries U1, U2 up to UN. Their union will be containing A. Okay. This happens because of compactness. Now here what you do is around Y you collect, you take the corresponding to these U1, there will be a neighborhood V1. Okay. So for U2 there will be a neighborhood V2 around Y. Now you consider this intersection of Vi I equal to 1 to U. Corresponding to these open neighborhoods U1, U2 up to UN, if you look at V1, V2 up to Vn, take their intersection, and then this intersection will be disjoint from this. Okay, this intersection will not have any common point with this union. That's how. And therefore, and this is an open neighborhood, and this is a finite number. We each open neighborhood. These are all open neighborhoods. These are finite in number. Intersection of finite number of open sets is open. So this is an open neighborhood. It's an open neighborhood of Y, and this is not entirely contained. This does not intersect with this. Therefore, it cannot intersect A. Therefore, this is entirely contained in the complement of A. That's how complement of A will be closed. Complement of A will be open. Therefore, A will be closed. Okay. Because of this becomes an interior point of complement of A. Okay. Therefore, A will be open. A complement will be open. Therefore, A is closed. Okay. And in metric spaces, this property, right? Here I'm taking open. You can take open spheres also here because you have metric. You can take open spheres of small enough radius or small radius. You can take open spheres around each xi. So out of this you get boundedness for A. Okay, that's how a compact set in a metric space has to be closed and bounded. Converse need not be true. You may have closed and boundedness, bounded sets in a space, but that space need not be metric. Okay. For example, if you take the cofinite topological spaces, they will not be metrizable. Okay. So you should be careful. And a converse will be true. Converse will be true in Rn. In Rn is a metric space. If you take closed and bounded sets, they will be compact. They'll be compact. That's what this Heine-Borel theorem is saying. Okay, Heine-Borel theorem says that a subset A of Rn is compact if and only if it is closed and bounded. From here to here, if you have a compact set in any metric space, that has to be closed and bounded. Regarding converse, if you have every closed and bounded set is compact, still that space need not be metrizable. Okay, that is the importance of topology. Okay, now I would like to present this theorem. That is proposition. That is proposition in the next chapter. That is 4.3.1. 4 proposition. Proposition 4.3.1. 4.3.1. Okay. Let if G is a closed proper subspace of a finite dimensional normal linear space N and epsilon is positive, there is an exception on the unit sphere such that infimum of norm of G minus X epsilon such that G belongs to G is greater than 1 minus epsilon. Okay, let me note down the statement. If G is a closed proper subspace of a finite dimensional normal linear space N, and epsilon is positive, there is an X epsilon on the unit sphere such that infimum of norm of G minus X epsilon such that G belongs to big G is greater than 1 minus is greater than 1 minus epsilon. Okay, let us prove this. If G is a closed proper subspace of a finite dimensional normal linear space and epsilon is any positive number, then there exists an X epsilon on the unit sphere such that infimum of these lengths is greater than 1 minus epsilon. Let us draw a figure. Okay. So, yeah, let's say we have a finite dimensional normal linear space. Okay, it can be Rn or something like that. Okay, its base is finite. It has a basis which is finite. When do you say linear space is finite dimensional? It has a basis, and that basis has finite number of elements. Okay, so that's what we mean by finite dimensional. Now, in this, let us take G. Let us take G in this. G is a proper subset, means for subspace. G is a closed proper subspace, means or in outside G you have some element. Okay, it is proper, means outside G you have some element. Okay, you have some element outside G, and this set G is closed, and it is a space also. It is a subspace. Okay, so this is closed also. This is closed, and so a closed subspace. As a vector space, this is a subspace. This is a subspace of V. Okay. Now what he says, you consider this infimum of G minus X epsilon. And if you take any epsilon positive, then there will be an X epsilon on the unit sphere. What is unit sphere? What is unit sphere? Unit sphere means around origin. Okay, around origin, the additive identity. You have to take a circle of radius. You have to take a circle of radius 1 unit. Okay, this is 1 unit. That is unit sphere. Right? That circle. In general, it is sphere. The sphere of radius 1 is called unit sphere. On that, you will have an element X epsilon, such that the distance between G belongs to G. Okay. For every G, this is true. Yeah, if you take a G here, and the distance between G and X epsilon, this will be right. He is taking the distance of G and X epsilon, the distance from G to X epsilon. The infimum of all these will be greater than 1 minus epsilon. Okay. So let's look at this again. If here G is a closed proper subspace of a finite dimensional vector space, and then if epsilon is any positive number, then there exists an X epsilon on the unit sphere such that for every G in G, this is for every G here, not outside. You should take inside. I'm sorry. You have to take inside. You have to take inside G. G must be taken inside. G must be taken inside. Small g must be taken inside G. Okay, these are all small g's. These are all small g's. So you look at the distance from X epsilon to small g. Of course, this may be G1, this may be G2, this may be G3. The small g is varying in capital G. Okay, so these lengths, you are taking the infimum of all these lengths. Okay, this is what G minus X epsilon means. This is the distance between G and X epsilon. The distance between this element and this element is given by norm. You take the infimum of all these lengths. Okay, that infimum will be greater than 1 minus epsilon. Okay, this conclusion helps you to show that if in a vector space, every closed and compact, if every closed and bounded set is compact in a vector space, then we can show that that vector space is finite dimensional. To prove that, this proposition helps us. Okay, okay. If you are given a normal linear space, if in this normal linear space every closed and bounded set is compact, then we can show that normal linear space is finite dimensional with the help of this proposition. Okay, that is the purpose of this proposition. Let us try to prove this. Okay, what we do is yeah. See, let us look at this. Let us take this as a D. Let D be equal to infimum of norm X minus G. Now of norm G minus X epsilon. Of norm, yeah. So let us take X in N minus G. Let X belongs to N minus G. Yeah. Yes. Here, this is X. Okay. This is X. X is this. X is an element in the complement of G. X is an element in the complement of G. For this X, you define norm X minus G. You look at norm X minus G. Let this small g vary over big G. Okay. So this is your X. Now you are collecting G from you are collecting small g from capital G. So you are looking at these lengths. Let me take different color. Yeah. You are looking at these lengths. Okay. Right. You take infimum of all of them. That you define as D. Okay. X is this one. It is in the complement of N minus G. And let small g vary over big G. And these are small j's. These are small j's. And you collect the lengths from G to X. Okay. This is the length. This is the distance between X and G. That is norm of X minus G. You collect all of them. Let your small g vary over big G. So you'll be getting different lengths. You take infimum of them. Define it as D. Okay. And here, because this is infimum, see, what happens if you consider D and D into 1 plus epsilon? Okay. D into 1 plus epsilon is greater than D. D into 1 plus epsilon, right? Let epsilon be positive. We are given epsilon positive, right? Right here, epsilon is in positive. You start with the positive epsilon. Okay. Now, this is D plus D epsilon. Okay. This is D plus D into epsilon. Now, this D is D positive. Epsilon is positive. How about D? How about D? Where is this X? Where is this X? Where is this X? This X is outside. This X is outside G. This X is outside G, and small g is varying in G. And because your G is closed, this D has to be a positive number. Okay, because your G is in big G and X is outside, and because your G is closed, is the closest subspace. Okay, this infimum has to be positive. Okay, it cannot be zero. It cannot be zero. This infimum has to be positive. Okay. Now, so this is a positive quantity, and this is positive. Epsilon is positive. 1 plus epsilon is positive. So this whole thing is positive. And because there is infimum between these two, if you take any value, okay, greater than this, there will be right. What is D? D is infimum of norm of X minus G, such that G belongs to big G. Okay. D is defined as infimum of norm of x minus g, where small g belongs to big G. Okay. Now, because, yeah. Now, see, for all these values, right? Norm x minus g may be greater than or equal to some values, m, right? Those may be small m's, right? Small m's, right? Small now x minus, it may be greater than or equal to m1, it may be greater than or equal to m2. This may be for all g's, Only we are allowing small g to vary. So as g varies, these may be varying. All of them may be equal to the same constant, maybe greater than or equal to the same constant, positive constant. All of these may be greater than or equal to m2, same positive constant, m2. Okay. Out of all these small mi's, you take the infimum, that is d. Okay. Now, because of d being infimum, if you take any value greater than this, there will be a point in this of which this value is strictly greater than that. Okay. So there will be a g naught. There exists a g naught belonging to g because of this. Your d is infimum of all this. Okay. If you take any value greater than this, if you take any value greater than this infimum, okay, for that value, if you right, it can be some d2. You call that value d2. There will be an element in this among these for which it is the d2 value. So this is taken for a suitable element from big G. So call it G naught. There will be an element G naught in small g naught in big G, so that this norm value is equal to d2. Okay, this happens because your d is infimum. Okay, from the definition of infimum, this happens. Now we construct this one. We construct this value x epsilon. You consider x epsilon is equal to x naught minus x minus g naught. Norm of this, no. This you have to take in the denominator. Okay. By this divided by norm x minus g naught. Okay. You divide this. You want, out of this, see, this is a positive quantity. This norm is positive. So this is non-zero. You can divide, its norm has to be positive because it's non-zero. It is positive. You can have it in the denominator. We want an element on the unit sphere. We want an element x epsilon on the unit sphere. Okay, on the unit sphere. This we want. So out of this, we generate a unit vector. Out of this, we generate a unit vector. It is this. You divide this vector by its norm. Okay, so this has norm 1. This is on the unit sphere. This is on the unit sphere. Okay. Now you consider any g in G for g belonging to G, for any g belonging to G, for any small g belonging to big G, you consider this norm of x epsilon minus G. You consider this. Okay. And this is what norm of, you write down x epsilon. This is x minus g naught by norm x minus g naught minus G. Okay. And this is what, this is equal to norm. You can multiply this by this. X minus g naught minus G into this one, norm x minus g naught. Okay. By norm x minus g naught. Norm. Okay. Now this is equal to, right? Norm x minus g naught. Right. Yeah. So can we regroup the, this can be taken out. This is 1 by norm x minus g naught into this is what you can take minus common. This is x minus norm of x minus of g naught plus g. Right? This can be written as norm of x minus g naught into g. Okay, I am taking minus out. So x minus of g naught comes, minus is out. So plus g into scalar. It is scalar times g. Okay, so norm ends. Now this is what where g is coming. Where from g is coming? Small g is coming from big G. Big G is a space. Big G is a closed space. Okay, so big G is a closed space. Right. So you have, because G is a subspace, right? Scalar times of that will also be present. This is a scalar product. It will be present in this. And G naught, where from G naught is coming? G naught is also coming from this space. This is a vector in space. This is a vector in subspace G, big G. This is a vector in subspace big G. B is a vector space. Therefore, some of these two vectors will be present in that. Okay. So this is because this is a vector, right? So this will be greater than or equal to, right? D, isn't it? Because this is a vector in G. Because since G naught plus norm x minus g naught into g is in big G. Okay, because yeah, this element is in big G. What, right? So this element x minus this element, this is some small g of the type of small g. So this distance will be greater than or equal to d because the d is infimum. So this thing will be greater than or equal to this numerator will be greater than or equal to small d. How about this one? Norm of x naught minus g. The reciprocal of this will be greater than the reciprocal of this. You bring to this to this side, take this to this side. So this is greater than d by d into 1 plus epsilon. 1 plus epsilon. Right? Now, the reciprocal of x minus g naught. This is x minus g naught. Right? Reciprocal of x minus g naught. So it comes to right hand side. This go to left hand side. 1 by d into 1 plus epsilon. 1 by d into 1 plus epsilon. Okay? This is what, right? What is this? This is equal to, let us simplify this. What this is equal to? D into 1 plus epsilon. Yeah, this can be, d can be written as d into 1 plus epsilon. You want 1 plus epsilon here, add 1 plus epsilon, right? D means d into 1. Epsilon is added, subtract epsilon by d into epsilon. Okay, so you can write d in terms of this. You want 1 plus epsilon, write 1 plus epsilon. D means d into 1. So plus epsilon is added, subtract that. Okay, so 1 plus epsilon by 1 plus epsilon is 1. So this is d cancel out. So it is 1 minus epsilon by 1 plus epsilon. Okay, so d into 1 plus epsilon, d into 1 plus epsilon cancel. You get 1 minus d into epsilon. D cancel out. So it is epsilon by 1 plus epsilon. What kind of a number is epsilon? Epsilon is positive. 1 plus epsilon is a number greater than 1. So this will be less than 1. 1 by 1 plus epsilon is less than 1. This is less than epsilon. And minus of that is greater than epsilon. So this is greater than 1 minus epsilon. Okay. Epsilon is positive. 1 plus epsilon is greater than 1. So 1 by 1 plus epsilon is less than 1 into epsilon is less than epsilon. Okay. Right. 1 plus epsilon is greater than 1 because epsilon is positive. Add 1 on both sides. 1 plus epsilon is greater than 1. And then reciprocal of this. You bring 1 to this side, this one. Take this to other side. 1 is greater than 1 by 1 plus epsilon. And multiply both sides. D is positive. Multiply both sides by d. So you have d is greater than d by 1 plus epsilon. You want d? No, you want epsilon. You multiply by epsilon on both sides. Okay. So you have epsilon is greater than epsilon by 1 plus epsilon. Okay, epsilon is positive. Multiply both sides by epsilon. So epsilon is greater than epsilon into this. Epsilon by 1 plus epsilon. Now you multiply on both sides by minus. So minus epsilon is less than minus epsilon by 1 plus epsilon. If you multiply both sides by negative, this reverses. Okay. Now you add 1 on both sides. You have 1 minus epsilon. 1 minus epsilon is less than 1 minus of this. Okay. That's how you have norm of this one. norm of this is greater than 1 minus epsilon. That is the conclusion. That is the conclusion of the proposition. Okay. So what we are doing, we are given a finite dimensional, normal linear space V. In that we are given a proper subspace, closed subspace G. Okay, and we have taken an element. Then we proved that on the unit sphere, in that space, on the unit sphere, you will get an element x epsilon, right? For every epsilon positive, you will get an element x epsilon on the unit sphere, such that this happens in form of norm of G minus x epsilon, as that G varies over big G is greater than 1 minus epsilon. Okay, you are letting this small g vary this big G, and you are looking at the distances between small g and x epsilon. Yeah, I'm sorry. Yeah, these are the distances between small g and x epsilon. Okay, you are looking at these one. Here, this is in form of these distances, these blue lines. Okay, this is G, this is x epsilon. So you are looking at the additional in form of these blue line segments. Okay, that in form of is greater than 1 minus epsilon. Okay, right? To prove this, how we proceeded? We assume that D is in form of all these. In form of norm of x minus G, G belongs to G. What is where is x? X is in the complement of G. G is proper. G is proper. So we took an element x in the complement of G, and we let small g vary in big G. Okay, we looked at the distances norm of x minus G. Okay, we looked at these red line segments. We took these in form of them. That is defined as small d. That is defined as small d. Because of this, we could get we considered a number greater than this, a number between these two. For the epsilon positive, we took a number between these two, and so we can get a small g in G, that is G naught, such that this value is equal to this norm value. Okay, right? And why we took like this means, if this form helps us to obtain 1 minus epsilon. If you simplify, this can be written like, right? If you can show that this is less than this, okay? And if you, this will be less than this. For epsilon positive, this will be less than this. And then from here, we are getting this one. Okay, so by multiplying by this, we are getting this. So this can be converted. Yeah, here d into 1 plus epsilon comes in the denominator. So this is a quantity greater than d. So between these two, you are able to obtain this norm of x minus g naught. Okay. So, but see, why means out of trial and error, out of geometry, all this comes. Out of geometry, all these, out of geometry, see, you have to look at these norm values, okay? And out of them, these expressions will be coming. So that's how you will be arriving at these. And then out of this, you define x epsilon. This is a vector on this unit sphere. And for this, you calculate it. You will now, for this, you want norm of x epsilon minus g. So you let small g vary over big G and calculated this. Okay, this becomes an element in G. Okay, numerator can be written as x minus an element in G. Now again, we will be applying this. So that brings in D. Because this is an element in big G, this norm of x minus this will be greater than D. Okay, so and then ultimately you can get this. So that is the basic idea. Okay, so this you have to remember, this proposition. This proposition will be used to prove that if in a vector space, every closed and compact set is closed and bounded set is compact, then that vector space is finite dimensional. This we prove in the next theorem. Tomorrow I will do that. Okay. So you please practice these concepts. Okay. Due to these classes, you are taught so many things. So you're right. There will be your mind might be getting very hot, heated. Okay. So you please try to read these portions that are covered in these classes, and Let's meet in the next class. Is it okay? Anything else you want? Hello. Hello.
Okay, sir.
Sir, compactness and completeness and okay, sir.
Yes, madam.
Compactness and completeness and okay, na, sir. Definition.
Definition in what?
Completeness and compactness.
No. Both are different. Both are
Okay.
different.
Okay.
See, there is printing mistake in your book. Both are different.
Avuna, sir.
There is printing mistake. Please correct. In the page 76 last line. In the page 76 last line. There, you please correct that. There is printing mistake. Page 76. Page 76. Last line. Last line. It is not complete. It is compact. It is printed complete. It should be compact. No. Both are different. This is compact. Okay, you please correct. Yeah, on page 76, last line, complete is printed. It should be compact. Okay. See, compactness means complete. Compactness means compactness is different. Completeness is different. Completeness means what? It speaks about convergence of Cauchy sequences. Okay. Yeah. The completeness means it speaks about the convergence of Cauchy sequences. Compactness in metric spaces. Right. This is the convergence of Cauchy sequences. Okay, and compactness means convergence of sequential compactness. Every sequence has convergent subsequence. Okay, in your topology course, you have proved that in a metric space, sequential compactness. Every sequential compactness means every sequence has a convergent subsequence. It is equivalent to compactness, and it is equivalent to finite intersection property. Okay, these three are equivalent in metric spaces. Okay, this is compactness. The completeness means it is convergence of Cauchy sequences. These two are different, not same. They are not same. Okay. Anything else? Hello. Maybe if you take uniform continuity, I think then if you club uniform continuity with this, then these two become equivalent. If you club uniform continuity with this, then these two may be equivalent. Otherwise, no. Okay. Right. Anything else? Friends, you have anything else to ask? So tomorrow shall we meet?
Yes, sir.
Okay. Goodbye. Thank you.
Excuse me,
Thank
sir.
you, sir.
Thank you, sir.
Thank you, sir.
Hello, sir.
Hello.
Sir,
Can we disperse?
sir, can you share some important questions for us?
Yes.
Can you share some important questions for us in the examination?
I'm not getting what you are saying.
Sir, can you share some important questions?
10 minutes, sir. I'm not getting
Sir.
your. Yeah, 10 minutes is there. Yes. You take
No,
rest
sir.
and go to the next class. Okay.
Sir, no, sir.
Oh.
Sir,
What
can you share some important questions?
What you are asking?
Exams in past purpose, important questions will be told to us, sir.
Bhavan Prasad Garu, what she is saying?
Important questions for exams.
Everything is important. Everything is important. First, you understand what we are saying. First, you try to understand what we have taught in these classes. Okay, then you can answer, you can pass out exam easily. If you can understand what we have taught, right, and if you practice these things, you can pass out exam easily. Okay, everything is important. How can you say so without understanding the terminology? How can you understand theorems? You cannot mug up. This is not any social studies paper. This is not any story. You have to understand each and every concept. Everything is important.
At
Okay?
least chapters also. Chapters, main chapters will be there.
You have to understand the terminology, definitions, okay, and then you should practice writing statements and their proofs, okay, for every theorem, lemma, and proposition. You have to practice. That is the only way. Everything is important. You take some old papers, you will know what will be important. Okay, right? Okay, bye. Tomorrow we'll meet.
Yes, sir.